picture this. You're standing on the coast, looking out at the horizon,
Yeah.
right? And you spot this sleek, ultra-modern commercial oil tanker just cutting through the water.
Oh, yeah, like one of those massive quarter-mile-long behemoths.
Exactly. I mean, we're talking about a total marvel of 21st century engineering here.
Yeah.
Hundreds of meters long, carrying the lifeblood of the global economy, just packed with, digital sensors and satellite comms.
Right.
But then as it gets closer, you notice something completely bizarre. Instead of a flat, streamlined deck, there are these massive, giant spinning towers jetting straight up into the sky.
It's quite the sight, honestly.
It really is. They look like towering industrial silos, sometimes 50 to 80 feet tall, just endlessly rotating. And it is this incredibly jarring visual. Honestly, it feels a bit like bolting a quirky 1920s physics experiment right onto a spaceship.
Yeah, it completely breaks our mental model of what cutting-edge maritime technology is, supposed to look like.
Right.
Because when you think of the future of global shipping and decarbonization, you generally expect invisible efficiencies. I mean, maybe hydrogen fuel cells or advanced AI route optimization algorithms.
Something under the hood.
Exactly. You certainly don't expect giant spinning metal tubes that look like they belong in some sort of steampunk graphic novel.
Yeah, it's wild. And to figure out why 21st century maritime shipping is suddenly relying on a century-old visual oddity, well, we're jumping into two incredibly detailed operational analyses today.
Yeah, these are from a publication called The Deep Draft.
Right, written by a serving master mariner, Captain Raghu Sharma. So our mission for this deep dive is to basically decode what these massive spinning cylinders, which are known as Flettner Rotors, by the way, what they actually are, how they generate forward thrust, and, well, the biggest question of all.
Do they actually deliver on their massive climate-saving promises, or, are they just a highly visible way to hack regulatory spreadsheets?
Exactly. That is the multi-million-dollar question.
Yeah.
So to understand why these towering cylinders are suddenly appearing on the decks of modern cargo ships, I guess we have to start by looking at the physics that makes them work.
We do. And the funny irony here is that the underlying science really hasn't changed a bit in over 100 years.
The ghost of 1922. Because Captain Sharma's analysis points out that these Flettner rotors, or rotor sails, they were first demonstrated at sea by Anton Flettner on a ship called the Burkel.
Yeah, back in 1922.
Right, and the whole system relies on a fluid dynamics concept called the Magnus effect.
Exactly. The Magnus effect is basically the operating principle behind this entire bizarre visual.
So how does it actually work?
Well, imagine that vertical cylinder mounted on the deck of the ship. It isn't just sitting there passively catching the breeze, right? It is actively being spun around its vertical axis by a dedicated electric motor.
Okay, so it's spinning.
Right, and as the wind flows across that rotating surface, the physical rotation of the cylinder actually changes the speed of the air moving around it.
Oh, wow.
Yeah. So on the side spinning with the wind, the airflow speeds up, and on the side spinning against the wind, the airflow slows down.
And, I mean, whenever we talk about airspeed in physics, we are fundamentally talking about pressure.
Yes, absolutely.
Like faster moving air creates lower pressure, while slower moving air creates higher pressure. So you end up with this pressure differential across that cylinder.
Exactly, and that pressure difference generates a really powerful aerodynamic force that pushes perpendicular to the airflow.
Okay, let me make this real for you listening. Think about baseball.
Yeah.
It's essentially the exact same physics that happens when a pitcher throws a vicious curveball.
Oh, that's a great comparison.
Right. Or like when a soccer player gets a free kick around a wall of defenders. The athlete puts a heavy spin on the ball. That spin creates a pressure difference in the air around it, and the ball just gets physically yanked sideways in midair.
That's exactly what's happening. The ship is essentially doing that, but with a massive industrial cylinder, and it uses that sideways aerodynamic yank to pull the entire vessel forward.
That is just so wild to me.
It's an elegant system.
Yeah.
That controlled, predictable lift is what makes it so fascinating. But there is a crucial distinction here between a Flettner rotor and a traditional canvas sail.
Which is what?
They don't just catch the wind blowing from behind. They respond to a very specific metric called apparent wind.
Wait, okay, so if it relies on apparent wind, which, just to clarify, is the combination of the true wind blowing across the ocean and the wind created by the vessel's own forward momentum, then the rotor only cares about the highly localized wind it experiences right there at deck level.
Precisely.
Which means if you're sailing directly into the wind, like hitting it on the nose, this massive sail is basically just an aerodynamic wall.
Yeah, that is the ultimate limitation of the physics. The rotor is strictly a secondary assist. It is entirely at the mercy of the wind angle.
So it's not a magic bullet.
Not at all. The Magnus effect provides incredibly strong forward lift in beam winds, meaning winds hitting the side of the ship at roughly a 90-degree angle.
Right, a crosswind.
But as that wind shifts toward the bow, the forward push just weakens rapidly. In a direct headwind or, in dead calm conditions, you can spin that cylinder as fast as you want, but you won't generate a single ounce of forward thrust.
Wow. So what happens then?
Well, the ship's main diesel propeller absolutely remains the primary source of power, always. The rotor just steps in to sort of offset the propulsive load when the ocean decides to cooperate.
Okay, I'm putting the pieces together here. If the physics are totally sound but incredibly fickle, and you still need your main massive diesel engine anyway, no wonder these things vanished for a century.
Exactly. They were just too situation dependent.
But that brings us to the multi-million-dollar question. Why are ship owners suddenly paying hundreds of thousands, sometimes over $1 million per unit, to bolt these things back onto their decks today?
Right. Well, the return of the Flettner rotor isn't actually driven by some sudden breakthrough in aerodynamics. We've moved from the mechanics of the wind to the mechanics of global regulation.
Ah, okay. The paperwork.
Essentially, yeah.
Yeah.
Shipping powers global trade, but it is under intense immediate pressure to decarbonize. The regulatory bodies have introduced these really specific, heavily enforced metrics.
The emissions report card.
Exactly.
Captain Sharma dives deep into these frameworks in his analysis.
Yeah.
He mentions the EEXI, which is the Energy Efficiency Existing Ship Index, and the CII, the Carbon Intensity Indicator.
Yeah, and these aren't just polite suggestions either.
Right. These are hard regulatory grades that dictate whether a ship is legally allowed to operate at certain speeds or even be chartered by major companies.
And the CII is particularly aggressive. It basically measures carbon emissions per cargo capacity over a nautical mile.
Okay.
Every single year, that required score gets stricter. If a ship gets a bad grade, it might be forced to physically limit its engine power just to burn less fuel.
Which means it sails slower.
Exactly, which means it makes less money.
Okay, but I have a hard time believing a multi-million-dollar shipping conglomerate is spending $1 million a pop on a spinning tower just for a PR stunt. The actual fuel savings must be the real driver here, right?
Well, this is where Captain Sharma introduces a really brilliant concept, measurement versus outcome.
Okay, break that down for me.
Modern compliance regimes reward measurable improvements in a ship's carbon intensity rating. They don't necessarily demand absolute systemic reductions in total fuel burned across the globe.
Wait, really?
Yeah. Once a score becomes a target, human nature dictates that optimization follows the metric. And the math of a Flettner rotor makes it an absolute superstar on a regulatory spreadsheet.
Okay, let's break down that spreadsheet math. How exactly does bolting a heavy electrically powered spinning tower onto a deck make the carbon per mile score plummet?
Think about the massive, 20,000 horsepower main diesel engine that pushes a cargo ship. It burns heavy fuel oil or marine diesel, which obviously has a massive carbon footprint.
It's a huge footprint.
Now, the Flettner rotor requires electricity to spin its motor. That electricity comes from the ship's auxiliary generators.
Which also burn fuel.
Yes, but the electrical power required to spin that cylinder is incredibly small compared to the massive propulsive power it offsets from the main engine when the wind hits that perfect beam angle.
Ah, I see. So, because the rotor generates so much thrust, the bridge can throttle back the massive main engine.
Nice.
And the main engine burns significantly less fuel, so the overall carbon output of the ship drops drastically, completely masking the fact that they still had to run an auxiliary diesel generator to power the spinning tower.
Exactly that. The net energy balance in the regulatory framework just looks fantastic. It improves the ship's CII rating, gives the company a crucial regulatory margin, and, it satisfies ESG audits from banks and charterers who want to see visible, quantifiable green investment.
Wow.
Even if, across an entire month-long voyage through wildly varying weather systems, the actual physical gallons of fuel saved in reality are somewhat modest.
Which brings up the signaling value. I mean, when a major retail brand is chartering a ship and wants to prove to its shareholders that it's using green logistics, nothing says we care about the environment, quite like a 50-foot spinning green tech tower right on the deck.
It is highly visible sustainability. Visibility is really the currency here.
But, as you hinted at, a spreadsheet model assumes constant favorable conditions.
Hmm.
It basically assumes the wind is always blowing from the perfect angle and the ship is sailing in a straight, uninterrupted line.
Right, which is never the case.
Because a ship doesn't sail on a spreadsheet. It sails in a volatile ocean, constrained by brutal commercial realities.
Yeah, out on the water, the crew faces what Captain Sharma calls the operating reality, and it is vastly different from the idealized paper model.
How so?
Well, ships don't operate in a vacuum. They are bound by strict charter party terms that dictate exact arrival times. They have to navigate traffic separation schemes, which are essentially these invisible, highly congested highways right on the ocean.
Right, they can't just go wherever the wind is best.
Exactly. Consider what that means for our fickle friend, the apparent wind. If a ship is navigating a traffic separation scheme in the English Channel and has to alter course by just 5 degrees to avoid a fishing fleet,
Or slow down by 2 knots to meet a tight pilotage window at the port of Rotterdam.
yes, the apparent wind shifts instantly.
And if it shifts out of that perfect crosswind sweet spot, well, the massive $1 million sail just becomes dead weight.
The rotor suddenly contributes very little. In those moments, a system that performs beautifully in a compliance model is literally just spinning its wheels at sea.
Wow.
This really highlights the concept of route dependence.
Route dependence makes perfect sense. I was actually trying to think of an everyday equivalent for you listening, and it's basically like buying a high-performance, track-ready sports car for your daily city commute.
Oh, yeah, that's spot on.
Like, the manufacturer's brochure says it can hit 200 miles per hour, and under perfect conditions, it absolutely can. But when you are stuck in stop-and-go traffic on a Tuesday morning, all that incredible engineering is just an expensive, heavy decoration.
If you have a bulk carrier doing a long, uninterrupted cross-ocean passage across the Pacific with steady trade winds, the rotor is a goldmine of opportunity. It functions like that sports car on an open track.
But if it's on a different route,
Right. If you have a vessel doing short hops, like a milk run around the Mediterranean, in and out of ports every 2 days, constantly changing course, the opportunity to use the physics is totally compressed.
let's look at the verified data to back that up, actually. Captain Sharma highlights a 1-year operational trial on a product tanker called the Maersk Pelican. Over 12 months, they saw an 8.2% fuel saving.
Which is great.
Yeah, that is a highly impressive verified number.
But then you contrast that with the wider industry averages. Organizations like DNV and Riviera report averages around 4.5 to 9%, generating roughly 100 to 150 kilowatts of propulsive assistance per rotor.
Okay, so there is real, tangible value there.
Oh, definitely. Flettner rotors definitively work. But in port-heavy stop-and-go environments, the rotor doesn't technically fail, it just becomes incidental.
Incidental, right?
Yeah, when a shipping company deploys these rotors across an entire fleet as a blanket proxy for environmental compliance, rather than carefully matching them to specific wind-favorable trade routes, their expectations completely detach from operational reality.
And the harsh reality doesn't even stop with shifting winds. Bolting a massive, spinning 50-foot tower to the deck of a working commercial ship introduces immense operational friction.
Oh, completely.
These are the hidden costs of integration that rarely ever make it into the headline fuel-saving numbers or, the glossy ESG press releases.
The physical boundaries alone are staggering. I mean, these structures consume massive amounts of premium deck space.
Right.
They add significant weight high above the deck, which actually alters the ship's center of gravity and affects its stability in heavy seas.
They also limit air draft, meaning the ship suddenly might not be able to clear certain bridges or specialized port infrastructure. And if the ship operates cargo cranes, the crew has to carefully swing these heavy swinging loads around a giant spinning silo without causing catastrophic damage.
It's a logistical nightmare, and the complexity compounds when we talk about navigation. These are tall, wide, opaque structures. They create massive blind sectors from the bridge wings.
Wait, blind sectors? You mean the navigating officers physically cannot see certain areas of the water around the ship?
Yes.
Paint a picture of what that actually looks like for a master mariner.
So imagine navigating a 300-meter oil tanker through the Strait of Malacca. It's one of the busiest, most congested waterways on the planet. Small fishing vessels and local ferries are darting everywhere.
Sounds chaotic.
It is. Now imagine standing on the bridge wing, trying to ensure you don't run over a smaller vessel, and a 50-foot spinning wall is completely blocking your line of sight to the starboard bow.
Oh, wow.
It is an incredibly stressful hazard. The extent of that visual obstruction actually has to be rigorously calculated and mitigated before the ship is even allowed to leave port.
That sounds genuinely terrifying in tight quarters.
Yeah.
And Captain Sharma mentions it messes with the instruments, too.
Oh yeah, cylindrical metal structures create severe radar shadowing and false reflections.
Wait, phantom returns. You mean the radar is telling the crew there's another massive ship right next to them in the fog, but the radar waves are actually just bouncing off their own spinning sail?
Yes, exactly. The radar interprets the spinning metal as an external contact.
That is insane.
And this isn't just an annoyance, it is a critical safety issue that requires formal class approval, specialized software filters, and coverage assessments. The crew has to learn to trust their instruments all over again while filtering out the noise created by their own green tech.
Wow. And on top of the stress, these things live in an incredibly hostile environment. They are constantly rotating machinery exposed to highly corrosive salt air, constant hull vibration from the main engine, and the brutal physical pounding of ocean storms.
Things break.
Yeah. Bearings wear out, sensors fail, control systems glitch.
Which brings us to the human element. The crew on a modern cargo ship is already dealing with a massive cognitive load. They are managing dangerous cargo, navigating complex weather systems, and adhering to strict commercial schedules.
They have enough to do.
Exactly. So the Flettner Rotor enters this environment as just another incredibly complex, salt-crusted machine in an already overcrowded decision space.
How does a tired crew actually manage that?
It connects to a very familiar dynamic in maritime automation. Captain Sharma actually compares rotor sails to ballast water treatment plants or exhaust gas cleaning scrubbers.
Wow.
These systems were all introduced with the best regulatory intentions, designed to save the environment. But on the ship, they enter a strict hierarchy of operational tasks. Navigating the ship safely and managing the cargo will always take absolute precedence.
Always. So if a sensor glitches or a bearing starts whining, troubleshooting the giant wind cylinder falls straight to the bottom of the to-do list.
Precisely. Unplanned downtime for a Flettner rotor rarely results in a catastrophic, newsworthy failure. It just looks quiet.
Like it.
Yeah, the crew might set highly conservative operating limits so they don't have to monitor the system as closely. Or, if a vibration alarm goes off during a storm, they will simply power the rotor down, lock it in place, and leave it inactive until the ship reaches a port with a specialized service technician.
And every single hour that rotor sits idle, the theoretical fuel savings on the regulatory spreadsheet just quietly erode.
Yep.
Because time spent diagnosing a glitchy spinning cylinder is time taken away from actually running the ship safely.
The ocean just doesn't care about the spreadsheet. Execution always determines the value.
That brings us perfectly to the core takeaway of Captain Sharma's analysis. Flettner rotors are a truly fascinating century-old application of the Magnus effect. They are a brilliant physics experiment that definitively works.
They do.
Under the right conditions, they generate massive aerodynamic lift and pull heavily laden cargo ships forward using the power of the wind.
Right. They are powerful tools, but they are not magic. Their value is fiercely dependent on the chosen trade route, the unpredictable nature of global weather systems, the physical limits of the ship's architecture, and, of course, the immense cognitive load placed on the human crew operating them.
So when you hear about the next massive wave of green tech or decarbonization initiatives, whether it's happening in global shipping, aviation, or even your own local power grid, you can't just look at the glossy corporate brochure or the highly optimized spreadsheet claims.
No, you really can't.
A perfect metric on a carbon intensity indicator report card might satisfy a regulatory body and look great on an ESG report, but the sea demands reality.
Because the environment doesn't benefit from a clever regulatory score. It only benefits from actual physical fuel being left unburnt.
Which leaves us with a final thought for you to mull over. As you picture that modern supertanker with those giant spinning 1920s towers bolted to its deck, dominating the visual space and boosting the company's compliance grade, ask yourself this.
What's the real cost?
Right. If we are designing the entire future of global trade around metrics that reward highly visible, highly quantifiable add-ons, what less visible but potentially much more impactful systemic efficiency measures are we completely ignoring simply because they don't look as good on a corporate emissions report card?
It is a question that, frankly, every single industry needs to be asking right now.
Absolutely. Thanks for joining us. We'll catch you on the next Deep Dive.